For the first problem of our review, we're supposed to use synthetic division to divide the polynomial. We were supposed to write your answer as quotient plus remainder over divisor. So when I set up my synthetic division table, and these can look different depending on how you do these, remember you put the 0 for your divisor over here in this column. So the 0 for x minus 1, if I set that equal to 0, I get 1. And most of you have memorized that you just change the sign, and that's okay, because that works every time. Across the top, you put the coefficients for your polynomial. So notice I have a coefficient for x to the 4th, which is 5, but I don't have a coefficient for x to the 3rd, so I need to put 0 to represent that. I have a coefficient for x squared, which is -2. I don't have a coefficient for x, which is 0, and I have a coefficient for my constant, which is -3. So again, 5x to the 4th plus 0x squared to the 3rd minus 2x squared plus 0x minus 3. Remember, the very first thing that happens after you get this set up is the 5 comes down directly, and then you do 1 times 5 equals 5. And I add that to my 0 to get 5. Then 1 times 5 equals 5. I add that to my -2 to get 3. 1 times 3 is 3. Added to 0 is 3. And 1 times 3 is 3. Added to -3 is 0. I tend to put a square or some kind of way to block off the last number in line, because remember, that's our remainder. And then you can count backwards. That's your constant, that's your x squared, and your x to the 3rd. So don't leave it like this. Please write it in the formal notation, which is quotient, 5x to the 3rd plus 5x squared plus 3x plus 3 plus remainder, which is 0, over the divisor, which is not 1, it's x minus 1. Okay. Now I realize that simplifies down to 5x to the 3rd plus 5x squared plus 3x plus 3. So full credit would be given to the quotient without writing the remainder over the divisor, since the remainder happens to be 0. Our next problem, use synthetic division to divide. So once again, I need a synthetic division table. Out front is the 0 for my divisor, which is 4. Again, you're changing the sign here. Then we need to stack the coefficients for our polynomial. Now, I do want you to check to make sure your polynomial is always in descending order. Notice I have an exponent of 4, then 3, then 2, then 1, then constant. In this case, every coefficient is represented. So I have a 1x to the 4th, a -3 with my x to the 3rd, a -5 with my x squared, a 6 as my x coefficient, and -3 as my constant. The first step is to bring the 1 directly down. 4 times 1 is 4, added to -3 is 1. 4 times 1 is 4, added to -5 is -1. 4 times -1 is -4, added to 6 is 2. 4 times 2 is 8, added to 3 is 5. So my result is, if you count backwards, that's constant x squared, x to the 3rd. Another way to think about this is if you take an x to the 4th and you divide it by an x to the 1st, your highest exponent is going to be an x to the 3rd. So you could start here and work your way down. So my answer is 1x to the 3rd, 1 not required, plus 1x squared minus x plus 2 plus 5 over the divisor up here, which is x minus 4. And that's your final result. Next problem, same story, except we're dividing with the x minus 1/2. So you have a fraction to deal with, which is probably not as bad as you're thinking. I change the sign of the divisor, or I write the 0 for the divisor, so positive 1/2 goes here. Make sure your exponents are in descending order. I got 3, 2, 1 constant, so we're good there. And notice they're all represented. So I have a 2 with my x to the 3rd, a -5 with my x squared, a 6x, and a 3. Notice no variables go in this. You're just using numbers only. The first number always comes down directly, 2. Now I'll multiply 1/2 times 2, which is 1. 1 plus -5 is -4. Now multiply 1/2 times -4. Now 1/2 times something is just 1/2 of it. So half of -4 is -2 plus 6 is 4. Half of 4 is 2 plus 3 is 5. So we're finished. I have a remainder of 5. Now remember, if I take an x to the third and I divide it by an x to the first, my highest exponent is going to be an x squared. So I have 2x squared minus 4x plus 4 plus a remainder of 5 over my divisor, which is x minus 1/2. Again, another way to think about that is that last number is the remainder, which means this is constant, this is x squared. So either way you think about that. Use synthetic division to divide. Okay, so once again, I have my synthetic division table. My divisor is x plus 6. The 0 for that is -6, or I change the sign. I need to make sure my polynomial is in descending order. I have a 6, a 5, a 4. There is no 3. Be careful of that. So there's a 0 x to the third in this problem. 2, 1 constant. So I have 4 for my x to the 6th, 20 for my x to the 5th, -24 for my x to the 4th, 0 for my x to the 3rd, -3 for my x squared, -13 for my x value, and finally a constant of 30. First number comes down, so 4 is directly down. -6 times 4 is -24. Added to 20 is -4. -6 times -4 is +24. Added to -24 is 0. -6 times 0 is 0, plus 0 is still 0. -6 times 0 is 0, plus -3 is -3. -6 times -3 is 18, plus -13 is 5. -6 times 5 is -30, plus 30 is 0. So this problem has a remainder of 0. If I take an x to the 6th and I divide it by an x to the 1st, that's going to give me an x to the 5th polynomial. Or you can count backwards, constant x squared, x to the 3rd, x to the 4th, x to the 5th. Don't leave it like that. Please write it in the proper order and notation. 4x to the 5th minus 4x to the 4th. You do not have to write 0x to the 3rd plus 0x squared, since that is just 0. So minus 3x plus 5 plus 0 over x plus 6. Again, this is just optional because it's 0. This is the true answer that I'm looking for in the end. For each polynomial, state the left and right end behavior. So either up to plus infinity or down to negative infinity. If you just say up and down or rising and falling, I will certainly give you credit for that. So we need to know what is the left side doing, what is the right side doing. This goes back to the leading coefficient test. And again, I tend to use the term end behavior. But you have to know the degree of the polynomial, and you have to know the leading coefficient of the polynomial to come up with this information. So the degree of this polynomial is 3. The leading coefficient is a +1. Anytime your degree is odd and you have a positive leading coefficient, every single time the left side is falling or going down, and the right side is rising or going up. So the next problem, let's take a look again at the degree. The degree is 5, so that's an odd number. The leading coefficient is the number in front of the degree, which is -5. And what's important there is that it's negative. Now, if you're odd and negative, it does opposite of this. So what I want you to remember is that odd means they're pointing in opposite directions. Okay, so this time the left side is going upward because of the negative, and the right side is going downward. So again, an odd degree, both odd numbers, 3 and 5, means they're pointing in opposite directions. Positive leading coefficient means the left's down and the right's up, just like an x to the 3rd graph. Okay, like this. A negative leading coefficient means the opposite. The left is up and the right is down, just like a negative x to the 3rd graph. For each polynomial, state the left and right end behavior. So again, in these lines, we need to either be putting up to plus infinity, the word up, upward, or rising, or down to negative infinity, down, downward, or falling. All of those are acceptable answers. So for this first polynomial, or C, we have a 3x to the fourth. Notice this polynomial is expanded. There's no multiplying out required for this, which means the degree is the highest exponent, which is 4 in this case, and the leading coefficient is the constant in front of the x to the fourth, the x value that gives you the degree, which is 3. Now what matters is this is even and positive. Your even and positive polynomials are always both pointing upward. Even always means they're pointing in the same direction, and positive means upward is that direction. So left is going to be up, right is going to be up, and then we are done with the requested question for that particular polynomial. Now for the next polynomial, what I want you to do is, first of all, find the degree, and then find the leading coefficient. Okay, so the degree of this polynomial, you're looking right here. Why? Again, because this polynomial is expanded already for you. There is no multiplying out that needs to be done. So the highest exponent is 6, so this is a degree 6. The leading coefficient is -4. Again, the important part is the degree is even, and you're dealing with a negative leading coefficient. Anytime you have both of these situations, you're dealing with the left side pointing downward and the right side also pointing downward. Remember, even means they're pointing in the same direction. Notice both of these problems on this page are pointing in the same direction because they have an even degree. For our last two problems, asking this, which is what is the left side doing, what's the right side doing, notice both of these are not in expanded form. Both of these polynomials are in factored form actually, so you can't just look at the highest power. So for 2e, the degree is not 3 because that's the highest power listed. That is not how that works. What you need to do is look at the degrees of each of these factors separately. So when you're looking at just this first x minus 1 to the third, that gives you an x to the third. So there's a degree 3 just for this part. There is an x squared here, x squared to the first, which is squared. And for this part is to the first. And when you multiply bases, you add the exponents together. So you're going to add this 3 plus this 2 plus this 1, and this is going to be a degree 6. So when you're thinking about this problem, this is a degree 6 with a leading coefficient. Well, imagine multiplying these constants together, a -2 times a 1 to the third times a 1 squared times a 1. Well, -2 times all these 1s is just -2. So again, even and a negative value means we're both downward on the left and on the right. Okay, so for the last problem, 2f, once again we have a polynomial called k of x that is not in expanded form. It is in factored form. So the degree is not the highest exponent. It is not 5. You have to consider there's 5 here, and then here you have x to the fourth to the third. So there's 12 there. Whenever you have a power raised to another power, you actually multiply those values together to get 12, and then you add when you multiply bases. So 5 plus 12 gives me a degree of 17 and a leading coefficient of 5. So you're talking an odd degree with a positive leading, which means the left side is pointing downward and the right side is pointing upward. Okay, so you need to know several things to do these problems. You need to know how to properly calculate the degree. Sometimes it's the highest exponent, and that's when the polynomial is expanded. Sometimes you have to add those exponents together when the polynomial is in factored form. The next thing you have to know is those 4 cases. So even degrees mean the sides are pointing in the same direction. Odd degrees means they're pointing in opposite directions. And then you have to determine which is up and which is down. Next problem we have to deal with here is matching. So what I want us to be able to do is take a polynomial and match it to its appropriate graph, which is probably going to be easier than you're thinking. I don't give any that are close together. What I want you to do is use the end behavior and possibly the x-intercepts if you need to help you do this problem. Okay, so when I look at I. P of x equals x squared minus 5x plus 6. I know you have an even degree because it's a degree 2 with a positive leading coefficient, which means both sides are going up. Do you see a polynomial in which both sides are going up? Well, I only see one. It's the c value right here. Okay, so this is number 1. Or you could go up here and say number 1 is c, whichever you feel more comfortable with. Okay, so our next polynomial is number 2, p of x is negative x minus 3 times x plus 1 times x plus 2 times x plus 5. This is in factored form. So the highest exponent is not just 1. That is not the degree. We would have to add all these together. So I've got 1 here, plus 1 here, plus 1 here, plus 1 here. So that is a degree 4, which is an even degree, and then a negative leading coefficient, which means both sides are pointing downward. I'm trying to find a polynomial where both sides are pointing downward, and notice that's D over here, so I could label that as number 2 if I'm matching, or I could go up here and say, hey, D is my number 2 polynomial. Okay, so let's look at number 3 polynomial, p of x equals x times x minus 2 times x minus 1 times x plus 2 times x plus 4. Notice that again is in factored form. So I have to determine my degree. So I have 1 from here, 1 from here, 1, 1, and 1. And when I would multiply all these x's together, I end up adding these exponents. So 1 plus 1 is 2, 3, 4, 5. So I have a degree 5. Now what matters about that is that it's an odd number. Okay, leading coefficient's a positive 1 because that's 1 times 1 times 1 times 1 times 1. So I'm going to say odd and positive, which means the left side is going down and the right side is pointing upward. Okay, this is our winner right here. Notice the left side over here is pointing down and the right side right here is pointing upward. Therefore, this is polynomial number 3, or I could go up here and say this is graph B, which means A must be 4. Now let's just don't jump in there and say it is. Let's make sure it is. Okay. Alright, so again, in factored form, we've got x times x times x, which would give me an x to the 3rd. So my degree is 3. Okay, which is odd, which means we're pointing in opposite directions. I have a negative leading coefficient. It's a negative 1 out there, which means my left side is pointing upward and my right side is pointing downward. Notice that is exactly what's going on in this polynomial. The left is pointing upward, the right is pointing downward, so I feel confident saying that this is polynomial number 4, or at the polynomial I could say this is graph A. Okay, now what we didn't use is the x-intercepts. Okay, now we didn't need to because these all had 4 separate end behaviors, but we could even check the x-intercepts. So let's just, for example, look at number 4. I have an x-intercept here. Looks to be negative 1, here at 2, and here at 3. Okay, well look, this is in factored form. If I set this equal to 0, I get an x-intercept of 2, negative 1, and 3 when I set those equal to 0. So that's not a surprise. That's just an additional, hey, look, this works. Let's check this out. Okay, I got an x-intercept of negative 4, negative 2, 0, 1, and 2. I have a lot of x-intercepts there. Okay, well look, over here, there's a 0 x-intercept there. That's 2, that's 1, that's negative 2, and that's negative 4. And that's exactly what we have marked here. So my confidence is even higher that this is the correct graph. On C, that might be a little bit harder to see. Okay, so this is 2, and it appears to be 3. But I could look at my polynomial up here, C. Now, notice that's not in factored form, so I can't even read the zeros directly off of this. I could factor it. I'm going to do that right over here. P of x multiplies to be 6, adds to be negative 5. That would be x minus 3 times x minus 2, which would give me 3 is a 0 and 2 is a 0, and that's exactly what I have here. And then my last polynomial, I have, it looks like a negative 5, a -2, a -1, and 3. Okay. Well, if I go to my blue over here, number 2, p of x, that 0 is -5. That's -2. That's -1. And that is 3. That matches exactly what we have here. So again, the x-intercepts did not have to be used, but we could have used only the x-intercepts and matched, or we could have used only the end behavior and matched. It was nice to do both because we're confident we are correct in our answer.